in recognition of benefits of ECC. Take a look at ECC implementation in C at Art of ECC site. Download the ECC code. Compile the code with AutoConfig tool. Install AutoConfig. Generate AutoConfig file. Rename the temporary file for configuration. Attempt to run AutoConfig. Encounter config errors. Add makefile statements in config file. Create AutoMakefile. Save AutoMake config file. Build AutoConfig again. Run AutoConfig. Build ECC application. Run ECC application. For payload length, we know from Hamming code a 4-bit message needs 3-bit ECC to correct one error. For correcting 2 errors, it needs more ECC bits with minimum of 15 bits in total. Specify the Galois field power of order 4 for allocation of field order of 16. Might as well use maximum correction strength 15 bits. Use moderate ECC bits for 2 errors. Inject 2 errors to corrupt the original message at location at 3rd and 10th bit stream. The execution of program does correct the errors and recover the original user message. Take a closer look at ECC Encoder. The cream of crop at encoder is the generation of remainder ECC by using linear feedback shift register. Error correction coding theory is conveniently built upon the concept of group, ring, and field. Group is a collection of elements. The name group was first introduced by Galois in the 1830s. For instance, there existed a group made by elements in the 3-bit binary register storage with members 0 through 7. The relation between elements is defined by its operator. Construct a table for addition operation. For 7 plus 1, it is 8. Since the register size is finite, the most significant bit is not registered into storage and is lost. Therefore, 7 plus 1 results in 0, not 8, because 8 is not an element of the set. However, in Galois language, the results can be arrived through division. The intermediate result is divided by the size of the group and takes the remainder as the final number, which guarantees it is within the set. This is known as modular arithmetic. More of the same, 7 plus 2. This is the entire enumeration table. A group has only one operation. However, it may expand flexibility by adding second operation. That is called ring. Addition table for ring, nothing has changed. New operator, multiplication. 5 multiplies 2 yields 2. 5 multiplies 5 is 1. This is complete multiplication table. Together, both addition and multiplication tables for ring. It gets interesting if we play the size of the ring. What if the ring size is not a nice full size 8? Instead of taking all elements, only subset of elements are selected to form a ring. This is called subring, a full ring with some defects. Let's pursue the subring. The hunt of defective subring is long. Looking at the subring size of 7, we can construct the addition table as usual. Similar principle for constructing multiplication table. This is the complete multiplication table of subring of size 7, which is a number cannot be reduced to the lower factor number. This irreducible prime number of the ring has major power. The powers. For a ring of prime size, there's at least one element whose consecutive power constitutes all the elements of the ring, and this spatial element is called ideal element. For instance, the element 3 is the ideal element of the ring, and its power constructs all elements in the field. Because of its repetitiveness, the ring is called cyclic. The power of this ring comes from its structural size being prime. The fellow element of the ring is analogous to the group of fellows, with Gandalf drop out in the early of journey.
Fly, you fools! Oops.
Thanks to Gandalf taking on the beast. of any size. The submarine gains its power and becomes invaluable and so priceless, so precious. Its preciousness comes from the Gandalf factor, another name for it, generator. The submarine with division operator is called field. A Galois field is directly constructed by a generator in the power form. The power form is good for multiplication, but not for addition operations. However, it can be represented in polynomial form for the easiness in computation. It is analogous to decimal number system. Each digit is the power of ideal element 10. For a given Galois field polynomial, let's find the Gandalf generator. Every Galois field has ideal elements. By definition, the evaluation with ideal elements on the Galois polynomials should be 0. Remember, the principal idea of the cyclic field is evaluated to unity, so it can be written in equality. Both equalities are congruent. Dividing them by principal ideal polynomial yields 0, meaning that the principal ideal polynomial is a generator. Let's construct a field with size 16. The principal generator has many factors, and any arbitrary factor polynomials can be used as a generator. Let's pick one. Using the polynomial as a generator, we can construct the Galois field. The generator polynomial with evaluation with ideal elements is 0. We may go ahead using the equality to construct the elements of the Galois field 16. This is the complete enumeration of the field. The construction of the field can be done efficiently by linear feedback shift register. Start with element 1 up to 14 and wrap it back to 1 again, and so forth. With generator at hand, let's make an error correction code that corrects 2 errors. Each generated polynomial has its own ideal elements, known as conjugacy. One minimal polynomial corrects 1 error, so we need 2 polynomials. Because the order of a generator is 8, the remainder ECC will be 8 bits. That leaves us with 7 bits for the user message. The last bit is just not used due to the defective size for cyclicality. To make room for ECC, the encoder first moves the user message out of the remainder area by multiplying the power of a generator polynomial, then divides by generator and take the remainder as the ECC and form the final code word for transmission. The Galois polynomial division is simply shifting and modular addition. The equivalent ops can be implemented with linear feedback shift register. The ECC is appended to data to form a code word. Let's step through the ECC generation. Build the ECCR. Attempt to compile. Fix build errors. Build alright. Specify user message. Set breakpoints. Start stepping through ECC generation.